Alrighty. So I'll just take down this presentation then, all right? And where are we here? I should know this. There we go. All right.
It's amazing.
Where is my? Maybe. Oh wow, this is a.
Maybe I should run out and get my Windows laptop.
No, it's okay. I just
All right.
need to see which way this thing goes. I heard this. Yeah. Okay.
So
Where is it?
MP4 files. It would be up at the
Okay.
top of the.
Where does this thing go? Okay, hold on. It's not showing up. The
Well,
drive
I
is.
saw
Yeah.
a list of files.
Yeah. Oh, you did?
Aren't we seeing like?
No, it should show up here if there's a USB.
Oh, okay.
Yeah. So when you plug it in, the thing is, it may be a wrong format. You said this is Windows, right? A Windows format? Yeah, it's probably not recognizing it. You'll need a Windows machine.
Okay, I will go get a Windows.
Yeah. Oh man, this thing is killer. All right.
Do it this way.
Okay. So you want me to just disconnect my laptop then?
I guess so.
Yeah. All right. Disconnect that. I'll leave your USB here.
Could play those.
Yeah, normally they can, but if it's some format that Windows can read that Mac can't, I think generally the formats they're compatible. But if you have a format that it's just older one, then it won't recognize it. All right. Yeah, there's a smaller step there. That's my power. Yeah.
Okay, where's the HDMI? Here's the HDMI.
Here's HDMI. Right.
All right.
And there's your USB. Yeah. Those things. Oh no, wait, that's upside down. Here.
Tom, you heard that?
Nope. All right, there you go. Sorry, what was that?
Thank you.
Right. Oh, right. Yeah,
Boy.
So this will get out of the way.
Oh, this technology gets in the way, huh? You know, SR? You gave everything away last year.
Yes, sir. I think we're.
Today, whatever you made today.
You having technical difficulties? Is it? What's up?
It's booting up, I guess.
Oh, it's booting up.
I guess.
His is a Mac as well.
Yeah.
If you want, I can get the USB, pop it in his, see if his is more
He
recent.
doesn't have a USB on his.
Oh, that's right. Yeah, his is USB-C. Does this,
But,
there you go. Right, you're up.
yeah, well, minimally. Let's see.
All right.
Probably, it's still booting up, still trying hard behind the scenes, you know?
Okay. All right, so I think you're in a good place now. I'll leave you to it.
Thank you.
All right.
And I copied only the slides. Copied only the slides.
Anyway, so tonight we have a joint meeting for the local chapter of the ACM, and we also have the IEEE Computer Society jointly hosting. And of course, the facility and the pizza are hosted by PayPal. So a big thank you to PayPal. And just so you know, we are video recording this meeting. And what I'm trying to bring up here is a little video for, there is an outside group, the City of Quebec in Canada, that is sponsoring the video recording and I guess the live streaming. I'm not sure if we're live streaming, but at least video recording. And so I'm struggling, my laptop is struggling to boot up. It looks like it ran out of power while I was headed in the bag. But in any case, the City of Quebec, Canada, how many people don't know where that is? Anybody, everybody know where that is? Canada. That's north somewhere. Need a passport. But the City of Quebec is generally, with their tech community, they are looking for technical people, so they have a job fair on November 23rd and 24th, so I guess that's right before Thanksgiving. And that's what we're struggling to show here. Toy Story next Tuesday. Oh, can you make that announcement?
Can we start a meeting?
Can we start the meeting?
I was trying to get your attention.
All right,
But
a 90-second announcement. The next ACM meeting will be next Tuesday evening at Facebook. It's going to be from Toy Story 4, the making of the Bo Peep character, with 4 people from Pixar in a panel. It's a free meeting. Go to meetup.com, search for SFBay ACM, and you'll find all the information. You must pre-register. And it's going to be a hoot.
So that was organized by the SIGGRAPH chapter of the ACM, the local Silicon Valley, as well as Facebook Disney group. And
Okay,
okay.
thank you very much, and that's.
I thought Bill wasn't ready with the video yet.
Well,
I'm almost there. Almost there.
I can't hear in that ear, so.
So, hold off for a second. There's no sense swapping out now.
I was waiting, I tried to.
Okay, here's, I have to apologize, excuse me. I have the today's introduction prepared, and before I drive out, I gave that to SR and gave him a wrong version of it. He doesn't know what I want to talk about. Now, everybody right now try to fix that up. Okay, everybody like our traditional volunteer group, everybody show up at last minute, try to fix the mistake I made. So thank you for everybody to just talk about, and let us start on, let the SR to start this meeting now.
Hold on. I'm up here. I'll finish this.
It's almost half an hour into the meeting, Bill.
Well, you could have started your announcements earlier, but, you know, we're doing this now. Can you guys grab the microphone?
Okay.
Right?
We tested these, I think.
Yep,
Yeah.
it's cold.
All right.
Anyway, at the Westin Hotel in downtown, across the street from the convention center, they're having this career fair on November 23 and 24. Thank you. So on November 23 and 24, they're having this fair, job fair. And I think that that's going to be it. That is going to be it. Sorry, we had some equipment incompatibilities. They had an audio spiel, but I'm not going to go through that. You can see the slide up here. And so on our meetup, we have an event. On the SFA-ACM meetup, we have an event up there for this. Okay, thank you.
Oh, sure, absolutely. I just hope I get the opportunity to speak. I'm just joking. I'll probably have to rush through things, so yeah.
You got a phone here.
But you know, that's mine, I think.
Good evening, welcome everybody. Sorry, it's almost a half an hour into the event and we haven't been ready yet to start the event. Apologies for that, to taking up time. I'll be very quick, we'll be done, right? So this is, it gives us a great pleasure to arrange events like this. Fortunately, I'm kind of sitting in the middle of ACM and IEEE, so I get to get the benefit of both to come and present the things here, organize the events here. And at PayPal, we have great pleasure in organizing such events. And a lot of people know about PayPal thing already. If, in case you don't, please use PayPal.
People have a competition right now from Facebook, right?
None. We're way behind. Okay. So this is the from last public announcement. This is what the numbers are. You can see that. Next, you can see the significant thing is $578 billion are flowing through the company. Okay, this is the total payment that is coming through. And there are 286 active accounts, out of which close to 60 million of them are merchants. And every account is a significant account because there's 29 transactions going through it, every account. Then how this is done is basically that's what the back end of it. We have a hybrid cloud situation here. We have on-prem, substantially big crowd. That's a private cloud with 32K servers and 10K applications running on them, and then 230K instances. We manage everything from here. This is designed and provisioned, and most of them are autonomous. Autonomous provisioning, autonomous management, and metering everything. And that is an engine that is driving this $578 billion. Of course, besides that, that infrastructure alone is not going to do anything unless we have some applications like one of the 10K applications, like a payments, risk modeling, so Tom will come into that. There are very significant ones that's what is really driving the company. And incidentally, we have one of the largest database, Teradata database on-prem. So this is what PayPal is, and we are very proud to support ACM and IEEE to bring in all these events. And I'll hand over to Elka, Chair for IEEE Computer Society Local Chapter here.
So I just have a few slides. First of all, thank you all for coming.
I lost that. Okay.
And thank you, ACM, for joining organizing this event together. So I just put very few slides. I'm Ilka Masada, Chair of IEEE Computer Society. We have Vishnu, Vice Chair, Rajiv, Raj Saktish as Secretary, and SR is our Treasurer. And we have some committee members. Kiran, Majaba, and Ardavan and Kujal is our webmaster. I just want to announce a few events to go quick. Tomorrow at SEMI, we are organizing the open house for Silicon Valley Engineering Council. IEEE Computer Society is a member of SVC, so we are organizing together this event. And we have a keynote speaker, it's Eric Sound, and he will have a great speech there. And event is 100% sponsored or paid by SEMI, so everybody is welcome to attend. And we have two more upcoming events. That one, and we have this December 11, another event. So this is organized by IEEE CIS, and we are co-sponsoring it as a relevant event to IEEE Computer Society members. So, and this one is going forward. We have a new Frontier in Computing NFIC key kind of conference that we are trying to change it from one track that has been for a long time one track to 4 track. So we are organizing this together with NATEA. So that's about what I have so far, and now I hand it to Liana. Thank you.
Thank you, Ika. And I was just noticed that one of your program chair is also one of them, our main cooperator for speakers for our ACM programs. And he was, I'm hoping we'll bring more speakers from the IEEE side of the industry to bring to the bigger audience. Specifically in the current status of AI take over all the industry, and everybody seems interested on that, and everybody interested in all the ethic and decision makings on programming. So people have to think about it. Let's see. Do I get the next page? All right. Okay. Here, that's advertising. That was a surprise to me. Okay. I think I think he would be happy because I'm doing that out of my order. That's from last meeting. And actually, we are introduced the industry positions on our website, and we're progress on that. They have a little bigger announcement later on. Just we're saying we are doing more to serve the community. Well, right now, okay, what else we have? Okay, here's an announcement, which is people already was talking about, and you probably get a little glimpse on everything, except I want to emphasize, tomorrow is SVEC sponsored a program with a keynote speaker on what?
Semi.
I know, academic. It's on robotics in psychology, right? Okay, so I'm still okay. The next meeting is at Facebook, and this panel speaker, hopefully to introduce more youngsters to join the computer science, which is sponsored by Pixar.
Well,
Okay.
they're speaking, Silicon Valley ACM SIGGRAPH.
Okay, yes, that's secret. That's he wants to say. Now, he used up his
And
time.
Facebook.
I'm doing the second time for him, okay? You should be happy. Now, this next event is, it's this job fair, because that's associated with the job positions for all the industry, and Quebec, from a government point of view, try to support something, support big companies to recruiting youngsters from Silicon Valley. So that's right before the Thanksgiving holiday. And so anybody, if you have people to come over to the Bay Area, bring them to the job fair, okay? Next one is our announcement, which is we're still looking for places for our own speakers on December 2nd, which is, it's on the FISR, it's also AI in vision recognition. And I think that's pretty good speaker over there. We got a lot of people signed up already, but we don't have space yet. If anybody have space, please contact me. Now, next one is December 3rd and 4th, or in the holiday season. Now, they have a second status of the AI sponsored by this same program chair to collect all the industry experts, try to give a second conference or teaching or whatever you call it, workshops in 2 days on December 3rd and 4th. So that's next announcement. How many time do I take? Here, now let's go back to the real stuff. Speaker, please repeat audience questions for the video recording. And audience, please keep your question down to the 30 second. Since everybody used up time, I will also announce that we do have a door prize today, and all the members of ACM chapter members and IEEE CS chapter members have a saying in their ticket or to in a door drawing, a door prize drawing. Okay, I think that's.
Yep.
I do have some introduction for this expert. He was
Yes,
there,
sir.
worked there for over 25 years on the same subject, and I don't have slides for him. So who is going to say something? Okay.
It's a pleasure for me to introduce Thomas. He has been with PayPal for quite some time, and he is in the risk team. And what they do is kind of really very special, trying to model the risky transactions. And so he is going to talk about a simulation of that model, because once whatever comes, they have to simulate it and make sure that the same kind of risk patterns don't repeat. So it's a great talk, and thank you very much for coming over, and I'll hand it over to Thomas, and he's going to take you from here.
Thank you.
Thank you, SR. Is this on, or can you guys hear me? Yeah. All right, great. So I had this working earlier on, so hopefully I won't have any technical difficulties. Let me just get plugged in here. I don't think it's on.
It's not on.
It's not on?
It's not on.
There's two of them, right? I think he has to turn the one on down there. Right, there's two of them. Can you guys hear me? No?
Gabriel?
Okay. All right. That's the sunset at Half Moon Bay if you're wondering where that is. Taken on the iPhone. Okay, great. Let me start off. Thank you all for being here. Sorry about the delay. I had budgeted probably about 15 minutes to an hour for this talk, and I know we're definitely kind of up against the clock, so I'll try and kind of speed along as fast as I can. I can take some questions slide by slide, but I think given the time, it'd be good if you can kind of keep them to the end. But if you do have a burning question that you must ask, sure, go ahead and ask it. So I'm here to talk about simulation platform architecture, right? And these are to simulate fraud models that both detect and deflect fraud. First off, just a quick call out to the mission of PayPal to reimagine money and democratize financial services. And I won't read through the rest of that. I'll leave that. Oh, it's stuck. Hold on. There we go. Okay. So SR went through some of the numbers. These are the official public numbers, and I want to bring this up. Oh, there's the sound. Okay. I want to bring this up so you'll get an idea of the scale we need to simulate, right? So I'll draw your attention to numbers, which is 578 billion in TPV, right? And then the next number then is the actual kind of transaction count that went through on 2018. So when I talk about simulation, that's the level and scale that we'll simulate. Yeah. This is the most recent Q3 results. I won't dwell on that too much. A great quarter. So into the agenda. When I was thinking about how to describe what the simulation platform does, right, I thought it was going to be difficult to describe it in isolation, right? So the approach I'm taking is that I want to first give you guys an overview of our risk fraud platform and how we detect and deflect fraud through kind of models and decisions and actions, right? So then once you have a good idea of what that system is, then I'll go into describing what simulation is and how simulation helps and accelerates that. Right. And then the best way to describe it is with a use case. So I kind of pick off one of our kind of simple yet still complicated under the hood use cases to explain what simulation is. Then I'll go into what our current state of a system was and what its legacy was, and then the need for platform thinking, right? To essentially revamp it and kind of pull it together into a robust platform rather than what we had a year or so ago, which is a series of point solutions. It all worked, but it didn't necessarily scale on kind of many dimensions. Now, when architects go and build platforms, the first thing they do is define architecture principles, which kind of guide you in the construction of a platform or whatever you want to build. Then from that, we'll go into what our target state architecture was that we defined, and then we can go straight into Q&A. Hopefully we'll have time for that. Right. So what is risk fraud management? Well, risk fraud management is a core asset for PayPal. It's both an enabler of our business. It supports our brand promise, and it's what makes us disruptive, unique, and allows us to innovate. All right, sorry, there's no slide clicker, and there we go. All right. So the risk platform itself is effectively a series of checkpoints, right? Now, what is a checkpoint? A checkpoint is essentially data, model compute, and that's where the data science goes in, coupled with decisions and then a resulting action, right? Now, very broadly speaking, in PayPal, we have kind of 6 categories of checkpoints, right? From all the way to the left are kind of more simple use cases, yet again, kind of complicated under the hood. We have our login checkpoint. That anytime you change anything on your profile, we'll basically have a checkpoint for that, and we'll kind of run models and we'll do a compute, right? Anytime you do anything with your financials, and then a financial is essentially, it's a credit card, it's a bank, anything that can kind of fund the payment, right? We have a lot of checkpoints around that. And then once you have a funding source added to your PayPal wallet, then the next thing people typically do is add funds. So when people are adding funds, we have checkpoints and models there to kind of deflect and detect any type of kind of fraud that could potentially happen. Then the next one here is essentially the move money checkpoint. So that's the classic one for PayPal, right? That's when you're sending money to a friend, where you're checking out on a merchant website that supports PayPal. We have a lot of checkpoints kind of all around there just to make sure that, when you move money, we verify, who's moving the money and actually the destination as well, and how it moves. Finally, all the way over to the right, we have our exit funds checkpoint. We have a lot of kind of modeling kind of around that. Exit funds is when you have money in your PayPal balance and you want to exit it out externally to a bank account or some other destination, right? There's a lot of focus on exit funds because once the money moves outside of the ecosystem, it's hard to get it back if it goes into the wrong hands, right? So as I was saying, checkpoint is data, model compute, decision, and then action, right? And an action can, let's say for the login example, we have this thing called an ATO model, right? An ATO model is essentially an account takeover, right? Now, in terms of an account takeover and a login, we want to make sure that the person who's logging in is indeed that person, right? And they're not being a victim of a social engineering attack like a phishing attack or a spear phishing attack, where essentially they can trick the user into getting those credentials, and then once they log in, they'll effectively take over the account, right? So they'll start kind of, draining money, exit funds, buying things, all sorts of nefarious activities. So there's a lot of focus on the login, right? And typical actions would be when somebody kind of logs in, are they who they say they are? So if they are, well, that's a pass, right? Then if you boil it down to a model compute into its simple essence, let's say you get a score of 0 to 9, right? 0 is, well, we're very confident of that person, and yes, well, we know John Doe is John Doe, and we'll let him in, right? On the other end of the scale, let's say it's a 9. We absolutely know this is a bad actor, and then we'll block them, right? Now, sometimes it's somewhere in between, right? And at the model, let's say, it would be a 4 or a 5. And in those cases, we'd have an action where we do some sort of step up, right? So that could be a 2-factor auth or asking questions and that. And then from that, then we'll decide, well, hey, is this actually a good actor or a bad actor, right? As you kind of progress to the right, the actions can get, they get more complicated. Let's say if you're trying to move a lot of money, you may hit like a limit for a know your customer or a CIP. That's when we'd go into the next level down kind of actions, right? We kind of queue it, ask for documentation. Once we get that and we really know, okay, yeah, this is the right person and they do have the ability to move this, then we would kind of release the hold. So that's essentially what risk platform is. It's a series of checkpoints. Each checkpoint is data, model compute, decision, and that'll result in some action being taken. So double clicking down into a checkpoint itself. So I mentioned it was data, right? And the 5 categories of data we have is essentially it's user data, it's transaction data, both transaction history and the current transaction as well, right? It's raw event data. it's a series of offline computed variables, right? So from all of your activity, of all of your history on PayPal, we build up essentially a profile. We have many offline applications where we compute kind of offline variables, and then we have them cached and ready to use when you go and make a transaction or when you kind of log in, right? Then the next category of data is the context data, which is the context of the transaction itself, right? So all those go into the next layer, which is to compute variables, feature variables, and data components. And the data component is, it's a more complicated or combination of feature variables and simple variables. Once they're computed, then they go into the model itself, right? And the model can be a classic machine learning model, deep learning, or an advanced kind of AI model, of which essentially when you compute it, you'll get a score, and then that leads into into a decision and then an action, as we discussed. Yeah. Right. Now, double clicking on the actual models itself, here's a sample of some of the models we have for some of the checkpoints here, right? So, we have consumer models, and then we have seller models, and then they're rolling up into the risk fraud domain. We have many domains for models, right? And what we're talking about here is essentially, the risk fraud ones. And if you go down into consumer, there's models for unauth activity, for ATO account takeover, stolen financials. So anytime you do anything on your profile or log in, we'll run those models, right, to see, well, hey, are you really who you say you are? Now, in green here is what we call a manifestation. So if the models are suboptimal or they're failing, and bad actors are kind of slipping through, we start seeing these sort of manifestations, right? So we start seeing kind of claims from our customers like, hey, I didn't make that payment, or I didn't move that money, right? And as you go over, right, you start seeing kind of chargebacks coming in, right? So if somebody's using a credit card to fund the payment and their account's kind of taken over, then they'll see these transactions popping up on their card, right? So then they'll ring their issuer and say, hey, I didn't make this. They do a chargeback, and then we get those chargebacks, and we start seeing them coming in, right? So they'd be kind of manifestations of, a model if it's kind of poorly performing. So with all that in mind, this is, I would say, a 10,000-foot view of our risk fraud platform. I'll kind of take it down the middle first. The clients of it are obviously PayPal.com, our core payment engine, our marketplaces that we support, and also adjacencies like PayPal and kind of Venmo, right? They all talk in to the risk system to effectively get decisions, right? So right at the top of the stack, we have a gateway. And then a gateway will kind of fan it out to one or more decision services or one or more services involved in the payment. So you could have a fraud decision, you could have a compliance AML kind of decision, you could also have a limits aspect of it as well if they're trying to make a payment that goes over kind of certain kind of thresholds, right? So the gateway will orchestrate that, right? Then it goes down to the decision layer. The decision layer will load some data, but it basically delegates most of it to the compute layer right off the bat, right? And it's the compute layer that essentially, loads in the data, loads in the offline variables and everything it needs to kind of compute its model. And when it gets the score, right, it will then kind of trickle it back through the decision layer that'll actually then make a decision, and that scoring then will be kind of, and decision will be kind of sent back to the client. And then it's the client application then that takes some action based on that. For the login example, if the model score is 0 to 9, if it's 9 and it's a bad actor, then that front end then will basically deny and block the user from logging in, right? As part of this, and as part of all of the activity on the site, core events get emitted. Right. And from these core events, we have our asynchronous data processing that also builds up asynchronous variables that are also used in model compute, and then they're kind of cached and stored in our data platform. An example of that would be simple kind of counter variables, how many times you've logged in a day, right? So typically we have kind of a profile of a user. They may log in once a day, twice a day, but then if we see a flurry of 100, 200,000, okay, we know something's gone awry there, right? So they're async variables, and they get more complex all the way down to kind of sliding windows that model past behavior versus kind of future behavior, right? All that gets stored in an online context, and it also gets piped to our offline context as well, right? Our Hadoop and also our Teradata. Then over to the right, everything that happens on site gets completely ETL'd to our data warehouse and then also our Hadoop. And this is where our offline models will kind of run and our offline variables get computed. And then they basically get piped back through our kind of Swift architecture to be kind of cached for an online context. So they're made available. So we try and push as much as possible to an offline compute. The analogy is kind of, hey, you'll pre-bake as much as possible for a cooking show, so you can just kind of take it out, right? It's pretty much the same thing here, right? We try and compute as much offline as possible. So we've done as much work as we can before an online kind of payment comes in. Because if you've done 80% of the work, well, hey, all you need to do kind of 20%, and that brings down the latency of a payment. Then in the compute stack, essentially to the right, kind of middling over, essentially is our AI platform, right? So if there is a model for a checkpoint that is AI or deep learning, it essentially makes a call out to our kind of GPU-enabled clusters, where essentially it'll run that deep learning or kind of AI model. It'll then return its inferencing back then to the core compute, and then that'll do a model ensemble, right? And then combine it to a score to send back to the decisioning layer. So that pretty much at a 10,000-foot level is essentially the architecture of the risk and fraud system. All right, oops. So here's a few quotes from our leaders, and I thought it'd be good to kind of read out a couple of quotes of what simulation is and its value before I go into describing it. So from Peretz, who's the head of our data science, simulation is a key competitive advantage, enabling PayPal to beat its peers by speeding artificial intelligence, machine learning, and model development. And from Gurinder, data science with simulation is world-class. Our systems can leverage years of real user and attack vector data in just one day, protecting our users and advancing our business promises. So that's the level of support we have from our leadership. Simulation is key to model development and fraud detection and deflection. So now that I'm halfway through the slides, I'll get to give my description of what simulation is. So simulation is effectively a historical replay of a live compute service, right? From analytically logged context data with carefully introduced and measured changes, right? To gauge the net effect of those changes by comparing them with the historically logged result, right? And then Sigma essentially is the code name of our new simulation platform. So what does that mean? And I think the best way of describing it is to go through the ATO example, which is the account takeover example, which is from the login checkpoint I kind of mentioned earlier, right? So let's say we see an ATO anomaly, right? So there's been a certain kind of level of account takeovers, and they can be from social engineering attacks like phishing, spear phishing, or various other kind of ingenious or nefarious ways of being able to kind of take over a person's account, right? So that's going to show up on essentially an incident report, and that's then going to go to a data scientist, right? And he's going to do his research and analytics, right? So he's going to go off, do the magic that they do, and then he's going to form a hypothesis, right? He'll say, well, oh, okay, so we let those bad actors in, right? And I think this changes to this model, or the analytic changes to whether it's a machine learning or deep learning model. I think this is going to do it, right? And he can be 100 or 110% confident, right? But then how confident are we as a company that his changes will actually block that type of fraud again, right? Now the resolution to an account takeover, that is relatively trivial. They call up customer service, they get control back of their account, right? So, but we want to prevent those instances from happening, right? Because once an account's take over, if you don't get it back, they can do some damage. Right. So essentially, the data scientist will make his changes to the model, right? And this is where simulation will come in, because you can test those changes, you can QA those changes, you can regress those changes. But when it comes down to changing a model, which get complex over time, how sure can you be that the model score will shift to a place where you can now detect that new attack vector or that new entity, right? And this essentially was where the simulation platform is leveraged the most, right? So essentially, what simulation does is it gets the analytically logged transactions around the time of the actual anomaly, right? So it gets that and it builds what we call a driver set, right? And a driver set is basically a large kind of file, right? Time bound of the time of the incident, right, with all of the transactions kind of there, right? So buried in those transactions are some of the anomalies that we've seen, right? So when you have this kind of driver set, right, which is essentially historical data, we have the inputs to that, we have all the context data that went in that, and then most importantly, we have the historical result of that, stamped with what we call a point in time or a kind of a PIT, right? So what the data scientist will do, he will then run a simulation. That driver set will be built. The model changes will then be deployed to the simulation kind of platform, because those models will be run on a model compute service, right? Then the simulation engine itself will pick up that driver set. It'll cycle through those transactions, right? And it will fire each one at the model service with the new analytic changes, right? And then what the data scientist is looking for is a model score shift in the direction around the transactions he knew that, hey, we thought they were good, but they were really kind of bad, right? So he's looking for the model to shift to a place, and let's say it's for a kind of login with the ATO, to kind of trend more to that 9, which we then say, well, hey, that's essentially a bad actor. And historically, the data scientists, they may not get it right first time, so there'll be several kind of iterations. So they'll kind of keep iterating and keep changing their model and keep running simulation until they get the model score to where it should be. And then once that is set, then effectively simulation has done its work. Right, so we've basically made the changes to the model, we've simulated it, and we've verified, yes, now we're actually going to catch that fraud, and then we basically roll that out to live, right? And the reason why that's so important is that, you may not see that fraud vector again for a couple of days, couple of hours, couple of weeks. So who knows when it's going to come back in again, right? So that's why simulation is critical to basically catch that, shift the score to where it should be, so then when it rolls out to live, when it does appear again, we'll catch it.
I have one question about
Sure.
clarification. So you said you give the incident to your data scientist who analyzes it to figure out what he thinks happened, adjusts the model, and then you play the same situation back to test whether his fix worked?
That's correct, yeah. And he's looking for a model score shift into a certain kind of range, right? So that example, and I am trivializing it by saying it's a 0 to 9, it's more like up into the thousands, right? But yeah, he'd be looking for it to kind of start trending closer to that kind of other end of the spectrum, like around the score of the 9, right? Or even a 7 or an 8, yeah.
Okay.
Sure.
Okay. Well, I won't go more.
Yep.
Do you have a large enough data set to prevent overfitting? I mean, how do you prevent things like that when you're training your model and with the data that you have?
Sorry, could you repeat the question?
Do you have a large enough data set to prevent things like overfitting when you're training your model? So you're using a certain data set and then...
Right. So,
Can you repeat the question?
yeah. He said, do we have a large enough training set to prevent overfitting?
Yes.
Did I get that right? Right. So, I'm not the data scientist, I'm more the platform architect that enables the data scientists, but yes, they do. And actually one of the use cases of the simulation platform is to actually run a simulation to generate the feature variables that would go into a training set, right? Because essentially, when they're building a new model, they'll have a list of kind of features they want in that kind of training set, right? Now those features may be new, right? But those features are built on basic kind of raw events that have been occurring in the system, right? So to get a large enough training set, they will actually run a simulation, right, with a modified kind of logic, right, to generate those feature variables, right? And then that they can build from the raw data. Well, we have 5-7 years worth of kind of raw data, so they can build a training set to as large as they need to train a model. Yep. Sure. Sorry, go ahead.
Yes, to add to the gentleman's question was, it's not a thing of overfitting, but what you need to do is do that anomaly detection that you have and make sure that in your simulation you have covered all variations around that anomaly, and don't expose that to your machine, your scientists, and then run it. You gave them the original one, but you have to do everything around it. Make sure that you
Right.
covered all the cases, otherwise you will have another similar attack vector. Obviously what the scientist has done will work. I mean, that's his job.
Right. Yep. So this talk is mostly about the simulation kind of architecture, right? Not the actual kind of core methodology of the data scientists that use it. So when they do the research, they pretty much do as you described, right?
On your side, you should do the other part to do around that anomaly to find every other space which the data scientists may not have looked at. And that's the
Yes, yeah, no, I agree. Yeah, and that's all about kind of building the driver set, right? So when you build a driver set, you build enough scenarios all around that, right, to basically kind of prevent it, right? And that driver set is what drives the simulation. Yep.
So how cheap is a simulation? For example, could you go on and sit there and just continually generate attacks on the simulation of your system at particular points in time? Is it cheap enough to do that, or is it so expensive that basically it's something that developers use as a tool and it requires a lot of cores and a lot of data in order to
Yeah. So we have, sorry, the question was like how expensive is simulation and how much you need to power it, right? So for our simulation use cases, we have two very kind of broad categories of use cases, right? One is to build training sets, right? So there we need as much data and much transaction history as they can get. And our long-term architecture goal is to be able to simulate 100 million of them in one day, right? So that actually takes quite a bit of horsepower, right? I think in our long-term architecture, we actually split out the hosting of the actual service with the model changes with the actual driving engine that actually drives the transactions to it, right? And I think to do that 100 million use case, which when you do the math, and I'll get to that in my capacity slide, it's almost moving about, to simulate 100 million transactions in a day, it's pretty much doing a throughput of 1.8 petabytes of data, right? Because when we build up each transaction for some of these heavy checkpoints, they're pretty heavy. Each transaction is about 73K. Now, that's just the transaction. So when that transaction goes into the model service to compute, it pulls lots of reference data. It pulls event histories. It pulls pre-computed data, right? And the average for our most heavy checkpoint is almost 2 meg of data, right? So you multiply the 73 by, and plus you add in the 2 meg per transaction as well. And then the outputted scores that they're interested in is about 1/24 of that, right? So when you add it all up, right, it's about 1.8 petabytes. So yeah, to do simulations of that scale is expensive. And I think the cluster that we would have for the host and model compute is an OpenStack cluster. We would use, I think it's up to 600 nodes to do that. And then on the Hadoop side, I think we're using about 150 kind of Hadoop nodes to power that, right? So yeah, large simulations, it does come at cost, but it adds kind of great value. So the ROI it's definitely there. On the other end of the spectrum, we have smaller use cases, and they're quite cheap to run, right? The driver set wouldn't be anywhere near close to 100 million. It's more about 10K, right? Those smaller use cases are not so much built for building a driver set or building a training set for a model. They're more to kind of verify kind of changes. And one example is, model score shift, right? If it's in a very narrow kind of case, then essentially when you make changes to the model, right, you want to make sure it's shifting in the right place. But the most commonly used use case for our smaller simulations is infrastructure changes, right? So if we have old infrastructure that we run models on, and then we create something, or make even changes to the same infrastructure, or build new infrastructure, right? Well, essentially it's the same model that's going to be computed on the old versus the new. So what we do is we take a slice of historical transactions on the old infrastructure, right? We deploy the model on the new infrastructure, and we run a simulation, right? And we get all those scores. Now then we go to the historical results for those transactions, and we do a compare. We pipe it through what we call an MTR, a match rate tool. So we're expecting the scores to be absolute kind of parity, right? Those ones are cheaper to do, but the long-term architecture and also business goals is to run them as fast as possible, right? Because that kind of flushes out lots of nuances in your infrastructure that wouldn't show up in a regular QA or a regular regression, right? So those ones, they want to run them as quickly as possible and as many as possible to flush out the issues as quickly as possible. Because once they're known, then engineers can fix them pretty rapidly, right? And then once they fix a batch of them, they'll submit a new build, a new simulation, flush out the next level, and you iteratively get to essentially a new infrastructure with all the good things that go with that new infrastructure that's at exact kind of parity with the old infrastructure. Because if you roll out new infrastructure for model compute, and it can be better, faster time to market, all that good stuff, but if the models are off what they used to be, then all of that good stuff on the new infrastructure is just thrown to the wind. Right, you're better off with your old infrastructure, because essentially if a model score shifts in the wrong direction, one or two bad things can happen at two extremes, right? You either let in bad actors, or just as bad, you actually block good actors. And when you're blocking good actors, you're blocking commerce, right? So both scenarios are bad when you have a model shift. Yeah. Next question.
What is the difference between simulation and testing? What you just narrated sounds to me more like a testing, but after the fact, you're verifying.
Yes, you're absolutely right. So the question is, what's the difference between testing and then simulation? So simulation, for the use case I just described, it's pretty much termed as advanced regression, right? So you'll do your QA, you'll do your testing, and then essentially the difference here is that you're taking real analytic logged live data, right? And you're replaying your service with the new changes on it, right? And then you're testing and matching up the scores with historical for what should be an exact kind of parity. So in essence, you're kind of right. It's a form of advanced regression that a regular regression wouldn't be able to do. Yeah. So I know we're running short on time, so I'll take more questions at the end. We still have a few slides to get through. Okay. All right, so the ATO, I've pretty much talked about the ATO, so I'll kind of skim past those. This is a kind of a visualization of it. So here I'll go into the workflow of a fraud risk simulation. And we've talked about some aspects of this before. So in order to simulate, it's all about the data, right? So if you don't have the data, you can't do simulation. It's just that simple, right? So typically, if we get a request to simulate a service that we've never simulated before, we basically have to ensure that we certify that service. And the key thing with certifying the service is to make sure we're analytic logging to our analytic zone all of the request data, the dependency data, and then most importantly, the output results of those kind of models and decisions, and we're point and timing them as well, right? So once that service has been run in production, and it's up to the requester how much data they want. Do they want a day? Do they want a week? Some want a few months, right? So you analytic log, then you have to persist and index those logs. And then to simulate, you basically build a driver set from those logs for the two time slices you want to run the simulation. And in an ATO or a login, if you see an anomaly, pretty much you want to get kind of data around that, right? You know it's around here, so you want to build a driver set, kind of around that kind of issue, right? Once the driver set is built, then the analytic changes from the data scientist typically go to a feature engineer, right? And the feature engineer will translate what the data scientist has done, either in R or Python, to essentially kind of Java code, because that's how we deploy our models, right? So once that's there and that's gone to the feature engineer, the modified build of the service is deployed to the simulation environment, then so is the driver set, and then simulation is basically kind of kicked off and run. Right? And then it'll run for some time, depending on how large or small. Right? And then typically the results are then kind of piped in for reporting. Right? And that reporting can take different forms depending on the use case. The classic one is like a match rate tool, or if it's going to build a training set for a model, we just deliver the results as is, and the data scientist takes that and extracts what they need from it to build their training set. So why simulation? Who would use it, and what's the value? So I think we've pretty much covered that. So it's simulation. It's critical to risk fraud, model development, variable development, and decision rule development. Right? It's used by developers, testers, so QA, advanced regression, right? Data scientists, modelers, and also rule writers. Rule writers are the ones that actually write the decisions that we talked about earlier. So it enables teams to iteratively debug, develop, and test their workflows. It simulates models, variables, and infrastructure changes, right? So this whole process, it greatly reduces the risk of releasing poor performing models or variables or rules to live, right? So we can release much higher quality, much better confidence, right? And then this net effect of this is it directly reduces fraud losses, giving PayPal's bottom line a kind of a positive lift. Okay, so we've talked about a couple of the use cases. The ones we've talked about is model performance, when they want to see a model score shift in a certain kind of direction, infrastructure migrations, building large kind of training sets for training kind of new models. Right? Also live variable synthesis, and this is directly related to our async variables and models that we'd build up. In terms of an async context, they're always built up of events that kind of asynchronously kind of flow through the system. So there will be kind of a logic there. So typically when you roll out that new variable compute logic, it takes a time to mature in live, right? So it'll take a month or 2 months to actually kind of build up a value that matures where it can then be used in a model, right? So typically the business doesn't want to wait 1 to 2 months or even a day, right? So what we would do is we'd run simulation on those events because we have all the historical live data in our simulation environment. So essentially for an async model or variable, we just basically replay that, and it actually matures the variable almost instantaneously. And then we can actually push those variables out where they can be used directly kind of in models, right? The other use cases are new feature verification, decision rule execution, and also compliance as well. Compliance is another big kind of consumer where we'd run AML models, limits, and watch lists and that. So that's another fairly big kind of use case, because if a watch list changes, they want to say, well, hey, based on all our transactions, well, what's the impact of those kind of new changes, right? How many transactions would I flag with these new models or lists where yesterday, I didn't, right? So that's critical for our compliance, which is pretty much the industry is calling kind of reg tech today. Okay, so the business goals we kind of touched on already. The long-term goal is to run 100 million in a day. And the current state, we kind of run about 5 million to 10 million before it kind of starts topping, hitting a ceiling, and wheel starts to come off the wagon. So we are a year or so into our journey, so we're basically kind of achieving those goals now. At the other end of the spectrum, where you want to run simulations as quick and as fast as possible, the business wants 10 to 20 minute kind of turnaround time, where before it would take a few hours, right? Because the more simulations you can get through, the more issues you can flush out, the more productive your data scientists and engineers will be, and the faster you can get changes out to live. So given the business goals and what simulation is and the growing number of use cases, we basically did a technology evaluation, and really what we found is that the platform we had was just an evolution of point solutions, and we really needed a platform to kind of tie it all together, right? Some of our early kind of solutions were basically just single-threaded kind of C++ batches where you take one driver set and it can just, cycle through kind of one at a time. So that's kind of bound to kind of one node, right? Then we evolved that into kind of Java and went multi-threaded, right? So then you can process in parallel, but then you're still bound to the one hardware node that kind of runs on, and that kind of starts topping out at a couple of hundred, kind of thousand, right? Then we evolved into using a big data technology with kind of Hadoop, and that showed kind of great promise because then we could really kind of scale wide, right? But then the first version of that, it had its downsides. It was, had some aspects of the implementation where it made it kind of brittle. You could scale it, but in certain scenarios it would break, and when it would break, it's very hard to just rerun that kind of one piece of it. So let's say you distribute it across 10 nodes, one node goes down, so one slice of the data is kind of gone, right? So a lot of the time it was very difficult to get that piece up and running. You had the other 90% of it, but you also really needed that 10%, and then that would result in, a lot of times, you just rerun the whole thing, so it's kind of a waste of kind of resources, right? Then the other aspect we found, kind of looking at our current state, is that our data tier was quite fragmented, so we needed to kind of pull that together as well. So this is a view of the Hadoop solution that I just talked about. And basically, you get a large driver set, you'd split it up into driver set fragments, and then each node would kind of take a fragment. And the logic was basically, or the engine was embedded in the mapper task. So what it would actually do is, it would start up a Jetty container, and then it would actually start up within the mapper task, and within that Jetty container, it would start the actual service that had the model kind of changes in it. And then in parallel, then that node would just cycle through its driver set fragment, right, and just kind of, fire all the transactions at the model service that was embedded in there, right? So it seemed like a nice idea at the time, and it worked, but in terms of brittleness, there's a lot of resource contention, right? Because on the one node, you had the model compute, which is very, very kind of, memory and also kind of compute heavy, competing with the engine that's trying to drive it as well, right? So a lot of times we get the Jetty would crash, or the model service crash, or it just deadlocked itself. It just got stuck, right? And this is kind of a visualization, like to the left, is the classic kind of Hadoop solution, right? So once the compute service dies or anything happens there, most times the data scientist says, well, I don't have confidence in the results. Yeah, you got 90% of it, but I need that other 10%, just rerun it, right? Going to our more long-term architecture, we kind of decoupled it, right? So we'd have the engine, rather than Hadoop, it would be run on Spark, right? And so it'd be a series of Spark executors. Rather than embedding the service you want to simulate within the executor itself, we actually decoupled that and deployed the service to an Altus pool. And Altus is nothing but our code name for our own kind of OpenStack kind of cluster, right? So you would deploy the service to an OpenStack cluster. There would be many nodes, right? And then you would deploy it then to Spark. Spark would break up the driver set, and they'd all run in parallel, and then you'd essentially hammer this OpenStack kind of cluster with the transactions. If one node would die, then essentially OpenStack just kind of takes that out of rotation, and then the driver just retries it, and then it should get it on the retry, right? So that worked very, very well, and then kind of removed the brittleness of the previous solution, but also still leverage like a big data approach where you can massively kind of scale. And that's how we get to the 100 million. It's just a matter of just adding enough hardware. Right. So with the current state kind of analysis, there was, the pain points are pretty much, in these categories. There was product, there was environmental, there was operational, ownership, architectural, so that's a collection of the point solutions. Essentially, you had all that, and then the conclusion, as I've mentioned, that we really need to tie it together into a robust platform, right? So this is a beautiful simulation product slide from my product partner. Looks great. Anytime I have a simulation presentation, I throw up this. This looks beautiful. All right, so continuing on with the architecture. So I know we're really kind of pressing up against the time, so I'll try and run through these as quickly as possible. These are principles that we, I'll take one question and I'll,
Really quick.
yeah.
Did you look at just Linux Slurm, like traditional HPC clusters, rather than Hadoop ecosystem for a resource management?
Can you repeat?
Sorry, could you repeat the question? Sorry.
Did you look at
Yeah.
just like traditional Linux, Slurm, HPC type computing for
Oh, right, I see.
simulation as opposed to Hadoop ecosystem for?
Yes, yes, yes. So the question is, do we look at kind of high performance compute for simulations, right? And the answer is, it's kind of one of those kind of yes and no answers. It really depends on the model you're simulating. If the model you're simulating is a deep learning or an AI type of model, when you compute it, we would basically, the compute service itself would then proxy a request to our high compute cluster within simulation environment. It would then run the AI or deep learning model. It would send the result back to the main compute, which is running on the OpenStack, right? And the OpenStack is where all the traditional kind of machine learning kind of models that don't need a high performance kind of compute. So yeah, we do have that for models that require it, right? And then to drive the simulation, basically to cycle through the driver set and fire the transactions, that's just traditional commodity kind of Hadoop, right? Because you don't need anything too special there, right? Yep. Okay, so these are the principles. I'll try and get through them as fast as I can. So the first principle is live parity. We want to have our simulation architecture and environment as close to live as we can possibly get, with the view that we'll never get an exact match, right? Because businesses' checkbooks are not that big, right? So you can't replicate entirely another kind of live, right? But we try and get it as close as possible, right? And the view there is that we view simulation as almost like a lab experiment, right? So with a lab experiment, you want it as clean room as possible. You don't want any contaminants in there, right? So if there's kind of difference in hardware, difference in software versions, difference in patches and that's all introducing kind of variance, right? So then when you run the simulation and the results come out, if they're not quite where the data scientist wants them to be, they're going to look at, well, hey, what was different, right? And if they see all these different kind of versions and patches and hardware and that, they kind of lose confidence, right? Because they say, well, hey, if there's any shift in the model score, I want that shift to be intentional because of the change I made to the model. I don't want it to be because of just some variance in your environment kind of introducing noise, right? So once they figure there is noise there, they'll typically throw away the results, no confidence, and then they want to fix that, and then essentially rerun it again, which just creates a lot of kind of churn, right? That's live party. Yep.
I know you don't want.
Sure.
Sorry, this is an important one.
Yep.
When they're striving for parity, I can understand that for verification, but what about model growth, model evolution? It should be ahead, right? Or you can have
that's
new simulation environment that's going to test new hypotheses, new ideas.
Agreed. Great question. So the question is, why are we striving for parity? Because there could be new use cases with new hardware. And you're absolutely right. So when there is a use case or a model that requires that new hardware or something new, we try and get that in the simulation environment, right? So then when we simulate to as close as it will be to live, even though live hasn't got that new hardware yet. And that really is aligning to striving for parity, because when a model does go out to live, it will have, let's say, a high performance compute, even though it's not there yet. We'd want to simulate it on high performance compute to see what it looks like. So yeah, great question. The next principle then is co-location. One of the issues with our previous collection of simulation kind of functions is that some functions may be in different data centers, right? Where in live, pretty much when you're running a model compute, it's kind of all co-located in the same kind of data center. So if things are split out, then things slow down very badly. The next principle is automation. In some of our legacy, there was manual steps in there. So we had a goal to automate everything. So there's no kind of manual things or that can drop. Next one is a common object data model. So collecting up a platform, which is a series of capabilities, we want to make sure that they're all kind of talking the same language, right? We want to put in a formal life cycle in there for simulation. There was differences between the different kind of use cases, so we kind of instituted that. Distributed processing, we've kind of talked before, so we want to leverage kind of big data to kind of distribute and horizontally scale as much as we can, right? The next one is in-memory pipelining, and that's where kind of Spark comes in. So if you remember from the previous slides, we do have checkpoints, and checkpoints are pretty much a real-time, online kind of compute, but it will kind of suck in as much offline kind of process data as possible, right? Our first iteration of simulation was just simulating the online process, right? But it shows great value to also simulate the offline compute. Right? Now, with the offline compute, it's not just one application, it's a series of applications, and they're pipelined. So the inputs is pretty much raw data, then the output gets fed into the next line of offline applications, which gets fed into the next one, and so on. And if you think about that, when you're dealing with the scale of hundreds of millions of transactions, you're just hitting the disk all the time. You're reading, you're writing, you're reading, you're writing. So a better way to do it is hold it in the big in-memory grid, right? So when one layer kind of runs, it writes it into memory, the next one picks it out of memory, does its compute, and so on, until you ultimately get to simulating the online kind of compute. So that's where in-memory pipeline is a key part of the architecture. The last one, which is probably one of the most important, is to move the analytic logging down to the infrastructure level, where before it was at the application level. So if we would make a change to a model or we'd introduce a new data element into the model, a developer would have to manually go in there and actually change the analytic logging to make sure that new piece of data got analytic logged. And for the most part, you know, they were disciplined and it would happen, but you do get instances where it just falls through the cracks, right? So then you have a hole in your data, right? A lot of times the data scientists can repair the data, but then that's extra churn and extra things they have to do. So we move the analytic logging right down to the infra level. So there's hooks in there. So every request that comes in, every call out to a dependency to get kind of data, and every request going back, there's hooks in from the infrastructure, so it automatically kind of logs that, so we don't get any, you know, data quality kind of issues. Okay, the capacity estimates, I won't dwell on these too much, we've already talked about it. So pretty much for that large simulation of 100 million, it's 1.8 to 2 petabytes worth of kind of network throughput and data processing. So that's the scale we're kind of dealing with, right? So with the target state architecture, and on the last few slides, so almost done. The target state architecture was quite big. So distilling it down into these kind of points was kind of, you know, took a lot of work. So the first thing with the simulation was we needed to get a dedicated environment, because simulations are running in a very large shared cluster with very large clients. We had payments, we had merchant, we had consumer. They all run like very, very large jobs on the cluster. And then we have a generic kind of DevOps, right? So simulation itself would take up a lot of resources, right? So when there was big jobs from other domains, they'd essentially starve us off and we're stuck in the queue, right? And then when we get to go, some of the simulations in the legacy, they could take a week. And a generic DevOps guy would come in and go, that's taking too long. Oh, let me sit it for a while. Come back a few hours later, oh, it's still running. Oh, next day it's still running. Oh, that must be hung. They go kill it, right? And then our simulation DevOps comes in and, it was running a minute ago, I went for coffee for 5 minutes and I come back and now it's dead, right? And typically when you kill them right in the middle, it affects the results, right? So then essentially you have to just restart that and that can take another week, right? So getting a dedicated cluster for this was paramount. And it did come with its trade-offs, because essentially all of the analytic log data gets logged to our main shared cluster. And we still build the driver sets on that cluster because that's where all of the data is. So we don't want to replicate that. That'd be too much effort. So we still build the driver sets on the shared cluster, and then we ship them over to our dedicated cluster, which we call Sigma, and then we run the simulation, and it has no interference at all. And then that also has an added benefit of no noise or no kind of shifts. And in addition, one big issue before is that if we need to patch the cluster, then we'd have to wait for a long time until they do an official stoppage, right? And then everybody stops, and then they'll update and patch, right? And then they can go along. Now we're in control of our own destiny. We can kind of, stop the queue, update it, and then let things kind of roll. No kind of waiting around. The next part of target state architecture we've talked about, basically leveraging a big data simulation engine. We'd started it off in the legacy. It showed great promise, but it was brittle. So we want to continue on with that. We want to rationalize our data tier. One of the issues where we were actually pulling a lot of event histories from a DR copy. Why? Well, we had no other source, right? So that's just kind of one example of where, hey, we get our own proper kind of read replica of transaction kind of histories, right? That nobody else touches. They don't bring it for downtime. They don't do failover testing, right, when you're trying to do a simulation. And that worked really well. The next aspect, we want to be multi-tenant. So not just simulate PayPal models and decisions. We want to simulate our adjacencies and models and decisions like Venmo and Paydiant. Infrastructure analytics logging, we've talked about that. A life cycle, data model, and then most important was putting in a governance model, because there's a lot of changes, right? So we want to be able to see kind of those changes and be able to kind of govern them and kind of control the flow, right? Other than basically getting changes that we didn't know about that breaks everything. The next part is to fully certify a service before we commit to simulating it, right? Because the analytic logging may be spotty or not there entirely, and they're saying, hey, why can't I simulate my service? Well, you don't have any data, right? So, it's all about the data at the end of the day. The other aspect is to get a full end-to-end simulation pipeline. We've kind of touched on that, because essentially an online model compute, it's really using about 70% offline computed data, right? Offline computed variables. Ideally, we want to simulate all that right from the raw data through all the offline applications, through the async applications, and into the model kind of online kind of compute, right? So we want to get a full kind of pipeline. Some of the issues we have in live are because they change an offline variable, nobody told anybody, and it kind of goes out, and the model is expecting it in one format, it's changed, and things break, right? So being able to kind of simulate all changes from start to finish is kind of key. The next one then is having a unified simulation dashboard with the current state and the legacy, a series of kind of point solutions. There's lots of tools here, there, and everywhere. We want to sweep all those up into kind of a unified kind of dashboard, so you go one place to submit your simulation, right? And we want to design the new system to better support new use cases. An example of that is graph simulation, and that is probably one of the most complicated things we need to simulate. So this is kind of a very high-level view of the new architecture, and I do realize it's 8:30, so this is the second last slide. So essentially, you'll have a UI. Everything we do with simulation, we want to put behind an API, so we can not just put a web interface, we can put a mobile web or a mobile interface kind of over it, right? Then have an orchestration layer, right, that properly schedules the simulation, and not just schedules it, but provisions the resources on Hadoop, on Spark, and also on our OpenStack kind of cluster, right? Because if you're running a large one, you need a lot of resources. You're running a small one, well, you don't need so much, right? Then it'll orchestrate essentially, the creation of the driver set, the deployment of the analytic build, and then the actual kind of running of the simulation and the monitoring of the actual simulation to make sure that it's healthy, right? Where before you'd run a big simulation, go away for a week, come back, is it done? Oh, maybe not. Right, where now, when you run a simulation, you get heartbeats, so you can basically track the health of it, right, and see when it's starting to slide and take remediation kind of action, right? And over to the right here is where all of our kind of data sources are, right? So we have dedicated for simulation. We're not kind of borrowing capacity from a DR off on the side or anything like that. We have dedicated kind of replicas for everything, and you can basically get a clean simulation to run with kind of zero kind of noise, right? And you can have very high confidence for the stakeholders. So once the simulation is run, then for certain use cases it'll deliver it in Kafka. Others it'll spool it to a file, and then once the results are there, depending on the use case, it would run through a match rate or just deliver it for a data science to build a training set. That's double clicking down the previous one. Since we're out of time, I'll kind of skip through this. But essentially, this is the accumulation of everything I've talked to up until this point. Right up at the top here, you have your live environment. It's analytic logging to our offline environment. Right? Then you get a user kind of coming in, he'll submit a request for a simulation, right? And this is with the assumption he's already made the changes to the analytic build, right? So then it will then call our PayPal build system with essentially a build ID that contains the service that has the models, right? It'll then deploy it then to essentially our OpenStack cluster, which is here, right? It'll also provision and deploy, well actually it doesn't deploy anything, the engine itself rarely kind of changes, right? So you'll deploy the model service to your OpenStack, and with your Hadoop, you're really just provisioning and reserving kind of resources to run your simulation depending on how big it is, how fast you want to get it done, right? And then essentially it just kicks it off, right? And it references its reference data to the far right, builds it in either Kafka or delivers the results, and it goes back then to the user and the requester, and that's pretty much it. Yep. And that's just a quick snapshot of our simulation metrics dashboard. Right, so these metrics are way up from what they were. So that really kind of goes to show the reliability and the robustness of the platform we put together. And now it's official time for Q&A. All right. Thank you all. Yes.
So I'm wondering if you could talk a little bit about the randomness that is involved in simulation, the degree to which you talked a lot about how simulation is replaying past history.
Yes,
but I'm
yes.
curious to what degree it generalizes to situations that are different than actual situations that occurred in history, or is it always just replaying history? No, it's that kind of general.
Yeah, that's a great question. And essentially, when you build a driver set, you're building it from historically logged transactions. And then the results are point-in-time kind of results. Where a data scientist would inject variability, and that's if they want it for their use case, is essentially in the driver set. So each transaction, each row of a driver set is essentially a transaction that the engine is going to pick up and it's going to fire at the model service with the changes, right? So in terms of variability and randomness, they can inject it on the row itself, right? Or they can have it in the model itself as well, right? And then essentially, it's really up to the data scientists how they want to interpret the results then. Yep. So it's two places, in the driver set itself or in the actual model itself. Yeah. Sure.
So I understand that the data scientists would have several models that they deploy over time. And in one of the slides you mentioned that they have to go and fix the analytical logs to map back to the object model. I may be saying it incorrectly, but I think that's what I understand.
Right, right.
So now don't you have to go back in time to fix the logs for all the older events also? Otherwise you have this notion of breaks in the models.
Oh yeah, if essentially there's issues in the analytic logging, right. So what'll happen is they'll actually kind of build a driver set. They'll have a kind of post process that then takes the driver set and it'll patch the data from more basic kind of data. And that's just additional kind of manual kind of step that it's hard to automate that, but that's typically what they do.
That's pretty compute intensive, right?
Yes, it is for sure. And the solution to that is make sure there's no holes or gaps in your kind of analytic kind of logging. Yeah.
Thank you for a great talk. Coming back to the question of models, since it's a pretty complex, how do you keep it modular enough that you're taking care of use cases like ATO and probably 1,000 other scenarios? So is it optimized so that you can simulate one area and also at the same time try to figure out what are the impacts for the other ones? How do you manage the process?
Right. That's a great question. So how do we? The question is, how granular it is, right? And how do we kind of control the simulation of just kind of one model versus kind of many models? In the current state where we are now, we kind of simulate on essentially a model compute service, right, which is kind of tied to a checkpoint. So a checkpoint will have a model compute service that has a set of models or a model ensemble pretty much for that checkpoint. And when we simulate all of that, right? Now, let's say there's 5 models in there and they just want to use kind of one. Well, yeah, the rest of it gets simulated. So part of, a long-term plan that's not here because it's basically pushed down in terms of priority from the businesses that, yes, we should be able to kind of simulate just one model in isolation, even if that service has 5 or 10, right? But in terms of priorities, that's kind of lower down, the priority list. But yeah, great question.
Thank you. Such a nice talk today. The question is more about the simulation, maybe aligned with the question that Jim asked.
Yep.
Or I would say extend to it is how long does the simulation process take today?
It depends. So the question is, how long does the simulation process today? And I guess the answer is, how long is a piece of string? Right? It depends on many factors, right? So it depends on how many transactions they want to simulate, for what checkpoint, because some checkpoints are lighter than other checkpoints. So our payments checkpoints, when we're doing kind of auth and capture and settlement, or even our kind of withdrawals and exits, they're kind of very, very heavy checkpoints. They have a lot of models. So those ones would take longer. So typically we'd run metrics and say, okay, well it takes so many 100 milliseconds to run this in live, right? Now, in terms of how fast you want it to run in simulation, it depends on how much nodes you can kind of provision, right? So some data scientists will say, hey, I want you to simulate this. I'm kind of going off for a couple of days, so I don't care. So when I'm back, you just get it. But if it's very high pressure and it's a bug and there's a lot of pressure on it, then we'd want to try and run that as fast as possible. So then it goes up on the priority. It would grab as much resources as it can, and you'd run it fast again. It's kind of hard to put an exact kind of time on it, but pretty much our system will calculate, okay, well, if you want it to complete in this time, you need, for this checkpoint, you need this many nodes on Hadoop and Spark, and you need this many nodes deployed to your kind of open stack. And if you can grab that, then we can kind of approximate the time that your simulation will be done in. Yeah.
Thank you.
Sure. Question at the back.
I would think that if you have a lot of seasonality, if you run to fix a problem that's operational questions.
Oh, sorry, this gentleman here had a question right on the back. If we can get the mic to him, that would be great.
If you're looking at a point of time in mid-November,
Yep.
and fix some problem, maybe that you actually screwed up what happened early Christmas morning.
Okay, so sorry, can you repeat the question? It was very difficult to hear, sorry. Yeah.
I would think you'd have a great deal of seasonality. So we're looking at a point in time around mid-November, like right now, making some adjustments to things so that they work correctly.
Mm-hmm.
What happens if that screws up the situation for early Christmas morning, which is probably a very different set of
Oh, right. Yep, great question. So the question is, due to seasonality, like peak shopping seasons, if you do want to make changes to your models and roll them out, right, will that affect your kind of, what happens if it kind of rolls out and it affects something in a negative way, right? So I think for our peak shopping seasons, we actually do have moratoriums. So we're actually not allowed to roll any changes out to the site unless we get, I think it's SVP approval. So it would have the change would have to be impactful enough that, and it would have to be risk related, where we'd run a simulation on it to verify, yes, it's good, but then we have to pretty much get SVP approval to roll it out. And then if you have that sort of visibility, you want to make sure it works. If not, simulate again and again and again until it does work and you're confident, and then you roll it out. Question? Yeah.
So does your framework allow you to proactively ever find things before they happen, like the Christmas example, where the ability to simulate lets you foresee that certain attacks may get through at Christmas if you don't do something in advance?
I don't think we so the question is, does simulation allow you to kind of foresee attacks that haven't happened yet, right? We don't have that use case yet because we always have a plentiful supply of attack vectors of people trying to do it. So, but yes, conceivably you could do that. And how you would simulate that is you're basically simulating, you have to build the driver set that has the right data with pretty much the right kind of transactions. And then in terms of the model, you'd probably have to make changes to the model to kind of simulate that and then kind of run it. So that's a way you could do it. But typically there's enough kind of rich source of innovative attack vectors that we never have to actually do that. But conceivably it could be done. Yes.
Thanks. So people talk a lot about speed. So from user experience point of view, we have a lot of problem for speed too. So when it is very slow, so people don't really know it's the analytics, the AI system problem, is the physical system has some issues, pattern also something. So for this simulation system, have you considered to look into the visibility or transparency of the underlying system?
Right. So the question is in terms of the speed, right? Have we kind of looked into kind of the visibility of the system? Yeah. So the simulation environment itself it's still in a HRZ kind of zone, but it's completely separate from live, right? So the running of a simulation, it doesn't affect any live traffic because we're always simulating some past event, right? That event can be just 5 minutes ago, but it's still historical. It's completely separated away from the live system. Now you can make changes to a model to maybe kind of speed it up, and you could simulate that, and you could get metrics on, well, hey, this model runs faster and still has the same score, and the score hasn't shifted. You could do that with the simulation system, and I think we've had some use cases that zoom in on the actual kind of latency for an actual model, and they also test when they're adding a model as well. They also have metrics around, well, how many milliseconds is it actually kind of adding to the overall kind of risk checkpoint kind of assessment. Yep. Sure.
Anybody else? If you still have questions, if you can come back later, I will be around. So I think we'll conclude here at this point. Thanks very much.
Okay, thank you all.
We have these two other things to do. First, there's going to be
We have a certificate for the speaker.
Oh, thank you.
Thank you for your talk. And
Thank you. Thank you, sir. Okay. Wait, I should show this as well.
Diana,
Right?
can you come?
Awesome.
Okay.
Right, thank you.
Thank you.
Thank you, folks.
Well, she wants to take Diana on.
Oh, sure.
You can get pictures from SR. We also have a raffle to do here, door prize.
Okay, listen. Okay, thank you so much.
Thank you.
No, I appreciate it.
All right, thank you.
Thank you.
You're going to do the honor.
I'm going to do the honors? Okay, sure. I'll just put this down here temporarily.
Okay, so do you want to pick a ticket out and,
Sure. Just call out the number.
so we'll blame you for it here, yeah?
All right,
The
yeah.
last three digits.
Yeah, you can put it all on me. The last tree is 163.
So 163, you're here, success there? Hey, finally won one. So you get the choice of book or t-shirt.
Architecting modern data platforms. How big's the t-shirt?
Okay. And you
All
want to
right.
pick another?
Sure. Shuffle it up a bit. All right. The number is 167. A little bit of space between them.
Yeah. You're going to simulate it.
Yeah, I think I need to simulate a more effective shuffle.
What's your pleasure? This one or this one? This one looks bigger.
Okay, then I'll take the bigger one.
Yeah.
Thank you.
You're welcome.
Okay, we need a short person for the next prize. All right, shuffle it around. Okay. 146.
That's good.
146.
Good separation.
That's the same number, is it?
The 6 is a common though.
I know, yeah, jeez.
Y'all recognize that from National Geographic or meerkats, huh? Okay, thank you.
All right, thank you very much. So Tom will be around if you have any questions.
Sure. Alrighty. Gonna recycle them. There we go.
Tomorrow we have open house at Semi. You're welcome to join. It's free event.
Oh, sure, yeah.
It will be great warm food.
Right.
At our open